Question 13. So we've got a diagram in the following arrangement: speaker here, 8.5 meters away from each other. You've got a position AB, which is 65 meters at a perpendicular distance from the center of the two speakers. And we have sound spreading out in this direction, sound spreading out in this direction, and the waves will interfere with one another. And we know from our notes that they will interfere constructively and destructively. And it says in the question, the two loudspeakers act as coherent sources. Okay, and that's where we start off. Explain what is meant by the term coherent sources. So, standard definition: the sources are coherent to one another when the waves emitted from the sources have a constant phase relationship to one another and have the same wavelength frequency throughout the transmission. Okay, so both of these have the same frequency or wavelength, and they are both have a constant phase relationship between each other. So one wave is continuously the same amount out of phase as the other one. Okay, so they are both essentially in phase or constant phase relationship with each other. And those are the two conditions for coherence. Second part to this question is: a sound engineer walks along AB, which is 65 meters from the speakers. So they move from here all the way to here. And what happens is the sound intensity rises and falls. So irregular rise and fall, rise and fall. So if you were to draw that out, so it rises, falls, rises, falls, rises, falls, rises, falls, rises, falls, etc. Okay, so what could explain the sound intensity rising and falling in the way that we have got here? Okay, so the waves leaving each source spread radially, so spread out. Okay, this means that there are regions where the waves from each source overlap and interfere. Okay, so they interfere and cross over one another. And that's the first mark. Walking along AB allows us to see this interference and the rise in sound intensity. So we look at that first. Corresponds to the waves constructively interfering. So we have to add in a bit extra, always a good thing to do. Talk about that. Path difference is a whole number of wavelengths, and the phase difference is that they are in phase with one another. So that's when we get constructive interference. Okay, path difference of a whole wavelength and in phase. Always mention that because often that's where the additional marks are. And the drop in intensity, the fall in intensity of sound corresponds to destructive interference. So the waves destructively interfere. And where does this happen? Where the waves that are overlapping are in antiphase with one another, and that corresponds to a path difference of order of half wavelength. So half wavelength, 1.5 wavelengths, 2.5, etc., etc. And that's where your marks are often. This could be a 5-mark question. So you mention the same points. The next part to this question, in the diagram, the loudspeakers are separated by 8.5 meters and are emitting sound waves with a wavelength. So the wavelength is given. Sound engineer stands in the position X, so stands here, which is exactly 65 meters away. So we can see that that's a 90-degree difference between 8.5 meters and 65 meters. And This is shown in the diagram below. And what we are trying to do here is we are to calculate the path difference between the two sounds. So sound travels from here to point X. Sound travels from this speaker also to point X, and they interfere at that particular point. Now, if the path difference, if the path difference corresponds to a whole number of wavelengths, so a whole number, a multiple of 0.553, then we'll know is constructive interference. And if it's out by order of half wavelengths, then it will be destructive interference. So let's find out what the path difference between the waves traveling from here to here to a wave from traveling from here to here. So the difference in path is this distance here minus this distance here. As we can see here, this is a right angle triangle. Pythagoras applies. So it's 8.5 squared plus 65 squared. This is the hypotenuse. So I've labeled it x. So that will be x equals root of 8.5 squared plus 65 squared. And that gives us 65.553 meters. Okay. Now, the path difference is that distance, which is x, which is equal to 65.553 meters. And that distance is 65. So when we take the difference, the path difference between the two, we get 0.553 meters, which is exactly one wavelength, as it says here. The wavelength is 0.553 meters. So the path difference of 0.553 is exactly equal to one wavelength difference in distance. So that means that the two waves that arrive at this point and interfere at this point are in phase with each other, and that will produce constructive interference. Okay, so how are the marks spread? As you can see, one for doing Pythagoras, working out the path difference, and then commenting on what type of interference and that we get.